Thank you, Darina. Basically, yeah, today we have a presentations of the course project for our course Introduction to Data Science and Analytics. And you basically know the rules. So each team has 12 to 15 minutes for presentations. And after that, we have some time for questions. And at the beginning, so each team in the order that was posted on Slack is going to share their screen, present, and after that we have time for Q&A. And the first, good luck with your presentations. And the first team to present is Team 6, please.
Yeah, could you please turn the first slide? Oh, reverse mode. First of all, hello to everyone. And yeah, and today we are going to present you outcomes of our research and result of our exciting journey through different ML algorithms, which we would like to use and to satisfy from our point of view, military needs. But before we start, we would like also to point out that we are the smallest team, and maybe next time it to be great to use our model to predict how many team members will be till the end. But nevertheless, let's proceed with our goal. Yeah, could you please next slide, Don? Yeah, thank you. So we started together with my two members. So we started to decide from business needs, from military needs. So at the beginning, we tried to understand and identify a real military problem and needs, and then try to solve them. So at the beginning, to identify military problems, we conducted a couple of interviews with militaries, analyzed public available data, articles, provided books, and so on. And as a result, we conclude that the modern war is online war. It's pretty known fact. It's obvious fact. And due to the fact all data is available online almost immediately, so everyone could use it, enemies and so on also could immediately use it. But also we conclude, or we understood, that there is a real problem to make decision as soon as possible without any delay immediately, due to the fact tactic situation on the battlefield could change dramatically in a couple of minutes, in a couple of seconds. It's really, really important in modern war. And as a result, we ended up with kind of idea. Yeah, next slide, please. Yeah, so solution. It's like it was our first sketch. It was like first idea to brainstorm. And what actually we can see here, and based on this like idea sketch, pretty silly, I would say, it's pretty simple. We started to think that we decided to divide all our battlefield on small pieces, and each pieces will be boundaries. And in online, using different ML approaches, which we will show in the next slides. But the most no, previous, but just here. And the main idea here that we constantly 24 hours need to aggregate data and analyze it, try to simulate battles, and based on all available data, simulate as much as possible. And based on this simulation, at once, 1 million, doesn't matter, we conclude and provide important information. For example, let me just give one use case. For example, accumulate data, try to analyze, we immediately simulate 1 million battles, and a result, we see that chance to win 90-100%. It means that authorities need to order attack. or maybe order to defense, or maybe to retreat, or maybe need to ask for help, and so on, so on. So that was like idea, and but the core here is just to use right ML model, and we started to our journey. For next slide, please. For sure, next we use not classical one. For sure, we started with classical ML, supervised machine learning algorithm, but it's for sure this idea due to the fact it's difficult to find applicable data. We try to aggregate data from games and so on, so on. But all this data is, first of all, it's biased on the one hand. On the other, it's not really relevant. So we moved to the another example. Another one, it's Monte Carlo. Yeah, so another one slide, please. And okay, just not to waste time, this we skip it. Next one. And here we see like, so we play with Monte Carlo, we set up like environment for Monte Carlo algorithm, try to play with this Monte Carlo. We see here time series for different teams. And we see that it almost lose or win. And on this time series graph, but the main idea and the main problem we faced, that it's difficult to use in Monte Carlo different setup environment. And the next step, we understand, to set up really applicable and useful and convenient for us environment, we need to use another approach. This approach is reinforcement learning, as single agent, as multi-agent, and actually this part will be shown in my team members. Andrew?
Yes, hello everyone. So as it was announced, we smoothly moved from Monte Carlo topic. We smoothly succeed. Sorry, some troubles with presentation. Okay.
Andrei, Mariana suggested that you can mute your
I see
laptop.
that Darina already.
Okay, can you hear me?
Yes.
Okay, so sorry. For this, so to proceed with presentation, as it was announced, the Monte Carlo algorithm, we moved smoothly from the Monte Carlo algorithm to reinforcement learning. Actually, Monte Carlo is just a subclass of the reinforcement learning algorithms. And Monte Carlo is still applicable to solve the prediction problem of the simulation. As we know that a little bit of the theory here, as we know, we can run like in a large number of the episodes, we can calculate the sample mean, and this way we can make predictions. But what is important, a part of the predictions, we have to solve the control problem. And to solve the control problem, we have to use other more advanced algorithms, and basically the control problem itself, it lies in the idea of the optimizing the policy to maximize the rewards. And for this problem, for this challenge, we have the set of Q-learning algorithms that can be applied in addition to the Monte Carlo to run the simulations. Along with that, we have so-called exploitation trade-off problem. And for this problem, Q-learning algorithms use the epsilon greedy approach to optimize and to explorate less when the epsilon decreases and exploitate the model more over time. So this is important to just like a theory part of the understanding of the Q-learning algorithms. Here I just ran the very basic implementation of the Q-learning algorithm, and like we can see, we can observe that that return increased over time, and basically while epsilon was decreasing. In addition to Q-learning and the basic Q-learning algorithm implemented in many libraries is a deep Q network algorithm. We used also some other algorithms to test, to train, and observe the outcomes. Two additional algorithms we used were A2C and PPO. So with this graph, it demonstrates the average mean over time. So like I ran up to 500,000 steps, so we can basically see that the PPO learned the best, and it's the smoothest algorithm among all, and like we don't see like any evidence of the overfit with PPO. Also, the length of the game increased. We played for the simulation. I personally used gym environments, in particular Atari environment for the battle simulation. Very simple battle simulation, to be honest. But yeah, as a starting point. So when I trained the model, I faced the overfit problem. So here in this particular slide, we can see that agent refuses to move, and basically it just stays in one position and does not explore. The problem with such environment like this is that it's very simple environment. It's basically all the games upon the learning stage, they just are dissimilar, like a large correlation causes this overfit. So to solve this problem, I tried to add some regularization, some noise to the observation spaces, and basically it's like made the agent to move and explore a better strategy. So with this, agent can play better and score more. Last set of recordings, I just compared how the model which is not trained and how the model which is trained play and score. Obviously, master scores better than newbie in this case, and yeah. So I'm handling all, and so the problem with gym environments is that it's very simple environments. They have the correlation between all the episodes, and it's really difficult to train the agent properly in such environments. So we decided that like we have to find some more heterogeneous and stochastic environment, or build a stochastic environment so we can train the agent in that environment. And I'm handing it over to Andriy, who will proceed with this part of the presentation.
Hi. I am third member and last member of Green Team. I will start my journey with, I started my journey with AP, and I thought it could be a good idea to use generative AI, specifically Llama 2 from Meta. It was interesting to work with. My idea was to generate some data in real time that we could use for placement of our battle entities, enemy entities, and so on. It is a default prompt that I made from Llama, like some coordinates, type, and few attributes. It is also possible to use my AP with custom prompt, and you can even ask everything whatever you want. For example, Warcraft enemies, and like it could be used in training. And I made it work on local Wi-Fi network. So you could, knowing your IP address and making a web request, you can retrieve the data in JSON format. Next. Previous. But there are many problems with generative AI. Sometimes output is incomplete. You can get instead of 100 outputs, you can get like 99.5, or you can get some additional text on top of your JSON and so on. So you have to check and recheck errors, and actually it is much easier to write like just simple random function and use it in your project. Then check and recheck it. Llama was fun to work with, but it's more complicated than it could be. Okay, next. From Andrei presentation, like Andrei, he used existing environments from gymnasium, and we decided that we, in order to proceed on our task, says that we have to use proximal policy optimization algorithm, and we have to make a new environment. I chose Unity for that for two reasons. Unity has multi-agent training, which is not so really available in Python. It is possible, but it's pretty complicated, and you can create any environment you want. It only depends on the time you have. And this agent from Battle City, it is reinforcement learning. You have observation spaces, some rewards system. I also used continuous actions for agent to decide what to do. Okay, next. Target is enemy tank and some zombie with AI. Okay, next. And environment is a hexagonal map, tiles. It is from Wargame and also from one nice Chinese paper. So my environment is one hexagon, but it could be expanded pretty easily. Okay, next. So on this slide, it's not easy to read, but like min reward is -1. It means that almost every episode agent didn't accomplish anything, and in the end, it will stuck. Next. Okay, done. Next. So agents decided it best to stay on place. So I had to make edits in observation space and continuous actions. Also edit rotations and some other stuff. Next. 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 Okay. So on TensorBoard, you can see a pretty good improvement. It's PPR algorithm, and like your reward is increasing. It's for 500,000 steps. Losses decreasing pretty much. So it is what we wanted to achieve, and we did it. Next. One of the models trained, it's not perfect. Next slide. But like it's physics here, and it's pretty chaos, but you can see that tanks, they reach the destination, which is another tank. So future in that project or any other could be, for example, using drones with lidars to scan environment in real time, import it in Unity, create your own environment, place entities, maybe using some delta API or another API to get coordinates and so on of you and present state is like heuristic method. It's a tank, some landscape, enemy tank with AI, and it could be changed. I need some more time to implement in previous model, but it is possible to do. Okay, thank you for your attention.
Okay, thank you to Team 6. Let's give Team 6 the round of the applause for their presentation. Any questions for Team 6? Okay, so I'll start with a question. So basically, do you think that you can make this practical? So combining the environment that you model in Unity, combining it with the reinforcement learning algorithms that you implemented. So what type of military battlefield operations you can practically implement? So you showed the visuals with what, 10 tanks probably? So at what level you think you can do it practically, and how long do you think it may take to implement this in Unity, to introduce the drone scanning, as you said, and yeah, how difficult, how long it can take to bring it to production, and at what level of the military operations, at the level of what types of military units? Дякую.
Thank you for your question. It is possible, but with some prerequisites. For example, you actually need coordinates of enemy and like observation and situational awareness of all your battlefield or your hexagon or whatever tile you choose, because using like using graphical neural networks, it will be much more difficult because you can simulate it, but it's almost impossible to make correlation between like real time and simulation, and it will have some other results. But with existing coordinates and landscape, it is possible. On my like estimation, it could take maybe 3 months and team from 2 to 4 members to make like simple model with landscape and so on, but maybe half a year or even more to make an automatization like system to get a landscape or photogrammetry from some source, you implement it, and so on and so on. And it's a good system to make an estimation or maybe best approach what to do in battlefield, but it's hard to tell how useful it could be on the real-time situation.
Yeah, thank you.
Don't, I'm sorry.
Yeah, please, questions.
Yeah,
So
if you don't mind,
to-
just add a couple of sentences to Andrew answer that, and also during at the beginning we explain, and maybe in here it's a good idea to bring more details. So first of all, in advance we could have already. It's pretty difficult task, but in advance we could already. In Unity, create environment, for example, for some region, and then during changes on battlefield, for example, trancheas or something like that, we could like change it immediately. But in advance, we already need to prepare. No, for example, we need to prepare for war. We need to have like on Unity some environment on the one hand, and on the other hand, I want to add that. We here talking about tactical, not strategy, but tactical operation. In this case, this simulation and this will be not so tough, I would say.
Okay, great. Thank you so much. So if you have questions, you can either unmute yourself and ask, or you can type your question in the chat for the teams. So anybody else questions to Team 6, to the green team? If not, let's give Team 6 another round of the applause. Thank you so much. And we are moving to the presentation of the Team 3.
Can you see the slides?
Yes.
Yeah, it's all right.
Okay, so we can start.
Yeah, so hi everyone. Today our team is going to tell you about our defense strategy optimization against a named aerial vehicles project. So we'll talk about why the current objective was selected, dive into the simulation system description and present conclusions. So firstly, I started by analyzing the literature about wargaming and intelligence analysis. The given literature underscored that simulating complex warfare operation traditionally demands years. So we couldn't afford such a long timeline due to nature of the war in Ukraine. That's why, after additional investigation, we focused on simulating the local anti-drone defense operation. So the whole world has been talking about the war in Ukraine as the first full-scale drone war. Considering the current situation on the front line, and according to comments from military representatives, we have spotted the specific problem: Lancet and Orlan attacking friendly camps. So the first assumption that we can make after analyzing open source literature is that the best protection against Orlan and Lancet is electromagnetic warfare. But in the real world, we have limited resources and must use them wisely. So we set another question: can we improve the protection of friendly camps by using intelligence analysis? So the short answer is yes. Our initial assumption and motivation was finding the best unit positioning in the camp by using a simulation system. An essential part of our project was to work with a predefined set of friendly units for cases when it is impossible to add more protection resources. But before we even started implementing simulation, we had to face the following challenges. First of all, environment has a critical influence on military machinery. Second, we had to map real-world characteristics into coefficients and describe them and create digital pictures of weapons and machinery. And we had to find mathematical reasoning for our conclusions to avoid result misinterpretation. So we want to show how these challenges were solved. And now I'll pass the mic to my teammate Vladislav.
Thank you. I will continue with covering the core elements of the simulation. So in our design, we focused on the simulating realistic scenarios. This includes integrating with external simulation awareness APIs for accurate inputs and replicating interactions with public APIs like weather services. For the MVP, we placed an emphasis on integrating key weather data. This choice is supported by extensive literature that underscores the profound impact of weather conditions on the behavior of drones and defense units. Specifically, we extracted temperature, wind speed, and various altitudes. Additionally, the simulation generates landscapes, simulating the parameters of specific defensive locations. Now moving on to the components of our simulation, we better start with overview of friendly units. They are divided into passive and active types. So the passive defenders include the key infrastructure, like headquarters, ammunition depots, which are critical points that we aim to defend. On the other hand, our active defenders comprising riflemen, electronic warframe, and etc. constitute a proactive force poised to identify and neutralize drone threats effectively. Both passive and active units have associated costs and amount of personnel. However, only active units can detect and engage enemies, which is reflected in their visibility range, fire range, and respective chances. Moving on to the attack units. Moving on to the attacks units, in our simulation, we focus on two main types, Lancet and Orlan. They are usually work in a pair, and are known for their effectiveness in the current war. We've used public information to add their key features into the simulation to create realistic scenarios. As our simulation is designed to record every event, we can easily analyze and visualize each simulation in detail. Here is a quick example how to understand the logic better. In this simulation, defense units are randomly placed by a specific positioning algorithm, while attacking units start at the map's edge. Red circles indicate attack ranges and gray circles show the detection ranges. This process begins with an Orlan scouting for targets. Once it identifies enough targets, it calls Lancets to strike the most important defense parts. The Lancets then move into attack while Orlans continue to monitor the area. Yeah, and that's it from the simulation core part. Now I will pass the mic to Bogdan for analytical part.
So analytics, why is it important? Suppose you're an army commander and you are about to conduct a military operation. You have two strategies and you perform 100 simulation for each of them. The first strategy leaves you with 0 losses, 99 out of 100 times, but in that one scenario, you lose all your units. Meanwhile, the second strategy always leads to the loss of 1 unit. And so you need to choose the strategy to use in the operation. The most natural would be to choose the strategy that has the lowest average losses. And so you have chosen the first strategy. And the next day, you use it to conduct your operation. The fortune was not on your side, and you have lost all your units. So maybe there are different ways to select the optimal strategy. The task we are solving has two intuitive objectives. The first one is to minimize the total cost loss. The second one is to minimize the total personal cost. Since our task is to find the best positioning of the defense units, we can formalize the problem in the following way. Let the capital X denote the set of positioning of the defense units. Capital S denote a set of environment states, that is the positions of an attacking units, weather conditions, and other factors we can control. Then the function U would be the total defense losses function. And so our task is to find its argument X star, which is the optimal positioning of defense units. Finding the optimal value of X is based on different decision criteria, so let's look over some of them. The most natural is Bayes-Laplace criterion. This one has been used by our commander. The optimal positioning under this criterion leads to the lowest average losses. The most pessimistic criterion is Minimax criterion. The optimal positioning under this criterion leads to the lowest maximum losses. If we want to maximize the probability of having the losses that are less than the pre-specified threshold, we should use the maximum likelihood criterion. And if we want to minimize the deviation from the minimum losses under each state of the environment, we should use Savage criterion. The last two criteria are the weighted sum of two criteria we have already discussed, and I think I should skip them. Let's look at the best positioning according to each of the criteria. We have performed thousands of simulations with 10 different positionings of the defense units. In the first picture, you can see the positioning of the units that are optimal under each criterion according to the first objective. And it is also the best under the maximum likelihood criterion for the second objective. The two other pictures show the optimal positioning for the second objective under respective criteria. And now let's move to the unit analysis. In this slide, we see the relative changes in losses after taking out one of the air defense system compared to the full set of units. From a strategic perspective, these insights are invaluable. The presence of an electronic warfare system is important for ensuring human safety, as as it can reduce casualties by up to threefold. On the other hand, deploying relatively cost-effective solutions like MPADS efficiently mitigates total losses. Such an analysis can guide us to prioritizing resource allocation with a focus on maximizing human safety through electronic warfare system, complemented by cost-effective options like MPADS. It underscores the importance of a balanced and multi-layered defense strategy for optimal effectiveness. Now let's again talk about positioning. As we look at this positioning, it's still being determined why precisely one on the left is better than one on the right, but it is. And the one on the left is 20 times better than the one on the right regarding cost losses. On the next slide, we will see details. This is a comparison example of medians of costs. On the left is the best positioning since it can defend with the most minor losses. On the right, it's the worst positioning example. So on these slides, sets are different friendly camp compositions with that contain a variety of units with different initial costs. If you combine all prices, the sum of the composition will be as listed: 1 million, 2 millions, 1 million, and 300,000. By comparing each set positioning minimum and maximum losses median, we can see that the difference that intelligent positioning can introduce. As for conclusions, we have reached the initial goal of creating a system that takes a set of units and environmental characteristics as input and returns the best positioning for such units and, in defense against UAVs. Our team successfully developed the simulation MVP as well as visualization extension to enhance the interpretation of simulation data. We established clear evaluation criteria and made their comparative assessment. Last but not least, we performed simulation results analysis and were able to derive meaningful insights about unit positioning and its importance on the battlefield. We believe that such local simulation can bring value without spending years on development. Thank you.
Thank you to Team 3. Let's give Team 3 the round of applause. Thank you so much. Any questions for Team 3? And again, you can unmute yourself, type your question in the chat, or any other way. Okay, I don't see questions, so let me ask a question. So you analyzed positioning of the units, and you basically said that electronic warfare is out of question, that's too expensive. So any other criteria that you can use, because probably changing positioning of the units may be difficult. Anything else that you can add to your analysis? Maybe using masking nets or just metal nets to defend the positions against the drones or something else. So if you cannot change the position, can you include something else in your analysis that allows you to do the same, but without repositioning the units?
So basically, reposition was basic idea, and by reposition, you can reposition a rifleman, for example. There are not only the static objects, there are also people with some weapons who can move around on the map. So that's why reposition was our objective. But as you said, and as we saw on the open sources, yes, these nets are very efficient. And actually, we have created such framework which can take this map as a characteristic of some specific unit, like additional characteristic of it. And this characteristic can improve its, for example, defense capabilities. And if we add characteristic, run the simulation and analyze results, we will actually see how the difference between with the net and without the net.
Thank you so much. Any other questions?
Also on the previous slides, you can see that electronic warfare is a really effective weapon, but also a man-portable air defense system can like decrease human casualties up to 1.5 times. This like man-portable, you can just move from one place to another, and it will be more efficient. So this was an objective of our simulation.
Yeah, thank you, Maxim. Any other questions for Team 3? If not, let's give Team 3 another round of the applause. Thank you so much for the great research and the great presentation. And let's move to the presentation of Team 2.
I suppose it's our time. 1 second.
Yeah, take your time.
So you should see my screen now. Yeah.
Yeah.
Okay. So hello, everyone, and welcome to our presentation. So let's first, let's just ask yourself about, have it been any one single day since the full-scale invasion that you haven't wanted to destroy all the Russian Black Sea fleet? So it's a Ukrainian moment, but as for me, I haven't had such a day. So, and that's why our team have decided to conduct research about naval drones operations and naval drones capabilities to destroy Russian warships. Also, in joke, we called it Operation Debuonization because our target was a Russian naval warship that is cruiser and rocket carrier of Kinzhal rockets, Kinzhal caliber rockets, Buyan M. So debuonization, yeah. So let's start. It's just our presentation structure, and I suppose that everyone knows why is it important, but let's remind you that Russia shells Ukrainian cities. Each day it shells our homes, it shells our hospitals, power plants, military facilities, factories, etc. So we can try to get an air defense for each such an object, but actually it's too expensive. And a more cheaper way is to destroy Russian attack capabilities, by naval drones that are relatively cheap. So yeah, that's why it is very, very important. So Markian, it's your turn.
Okay, thank you, Andriy. So our team devised a solution and actually the whole environment where the key agents were the battleship that was the target and also the drones that hunted this ship. We run genetic algorithm simulation to optimize our scenario and to find the best setup of our drones that would maximize damage that they deal to the ship and also minimize the cost of the operation. Next slide, please. So actually our team consisted of 5 members, the Andriy that you already know, me, also Tatiana, Mikita, and Eduard. Andriy was responsible for desktop application development and evaluation of the results. I was responsible for creation of the ship and cannon logic. Tatiana was responsible for implementation of genetic algorithm for our configuration optimization. Mikita made the logic for our configuration, and the Eduard created the logic for critical parts of the ship, such as engines, ammunition, storages, and gas canister sector. Next slide, please. So our core technologies consisted of these four ones. Actually, the whole environment was created using Pygame with addition of the NumPy vectors. The simulation were run in the Jupyter Notebook, and also the analysis and evaluations were made there. And the desktop application were created using Kinter. Our core objects that we aimed to represent as accurate as possible were, as was said, the battleship and the sea drones. The model of the ship is the known Russian air missile ship, Buyan M. And as the models of the drones were Megura and Sia Baby, are well-known Ukrainian drones models. Next slide, please. And the next slide, and I will pass the word to the Eduard.
Here is our main warship that participated in our simulation is Buyan M. He has two type of weapons. It's artillery and machine guns. They have limited area of action, and that weapon will try to shut down the drone when the drone gets to the area of action. These weapons. Next slide. Yes. Here is critical parts of the warship. Is in our we assume that if a drone gets critical points or critical parts, in our case it's like storage, ammo storage or engine. They get additional critical damage, and some, for example, if a drone gets the engine, the ship will punish it by the speed. Next, please.
Yeah, so in our simulation model, we are trying to find the optimal drone formation for our drone fleet. And so the first option was to generate the drones in a form of a group. Those resemble kind of metrics with a small distance between different drones that pursue the selected target on the ship as a group. The second option is a random formation, which basically means that we generate the drone fleet on a safe distance from a ship in random points, which introduces some unpredictability in targeting. And the third option is, we called it a star. So it resembles a kind of a circle around a ship, which ensures that all of the parts of the ship could be covered. Yeah, next slide, please. As for the targets on the ship, the first target picking strategy was closest ship point. So basically, before making any further move, a drone calculates the closest point on the ship. The second option is picking the closest critical part of the ship on each movement. And the third option was to ensure that each critical point on the ship is being addressed. So a certain proportion of drones is defined in our configuration, and the drones that are left out are used as decoys to take the attention of the ship. So yeah, next slide, please.
Yeah, so the next challenge was to evaluate different drone strategies, different formation strategies, different target strategies, and different drone types. So we have had Magura and Seababy, and also different types of Maguras and Seababys. So we used 4 key elements of metrics that are key in operation evaluation as a whole. So the first one is game win. It's about probability of winning a game. So destroying the Buyan M class warship with specific configuration. The second is drones left percentage. It's it's quite kind of an optional parameter because it's valuable when we want to conduct not only one operation but several operations in a row. So then we don't want to spend all our drones for one ship, like for Buyan M class, for example. And for example, we can wait for some rescue ship or something that to damage more Russian warships. The third one is about ship damage percentage, so it's quite correlated with game win, but at the same time, maybe sometimes it's enough or even more valuable just to damage the warship, not to destroy it fully. Maybe some resources will be spent by Russians on this on its reconstruction and so on. And the fourth one is about drones cost. So we don't want to spend all the Ukrainian budget for our drones to destroy the warship. So we try to use as cheap drones, or maybe many cheap drones, or maybe less number of more explosive but more expensive ones. So it's also used in our evaluation, and the person who uses our app can weight those elements as the domain, his domain knowledge leads him, so that what is more valuable for him will just get more weight and will be more important for optimization. So let's see how our user interface works. So here it is. So the first page is optimization page. So we can take some number of optimization iterations, some optimum cost of drones, and also weights for our parts. And we click optimize, and our genetic algorithm starts working. So how it will end working. 1 second. Yeah, so we have got some parameters, we have got some measures. For example, ship destroyed probability is 0 here. Ship damage percentage is 70%, expected here. Drone's cost is 1,100 when optimum is 1,200. And also we have got parameters the formations group, and we use Seababy with 500 kilograms of explosive elements and so on. Yeah, so we have got it. We can simulate our attack of our drones on the warship with those parameters. So these are optimal with those weights, and optimal among those we search. Yeah, so also there is simulation page when we can just use different parameters but enter them manually. And also one of our key values was to make this application as so we can enter almost any parameter we have in our simulation here in settings, and it can change the simulation completely. So we just don't have enough domain knowledge about new Ukrainian drones or maybe some Russian ships capabilities, but at the same time we can give our app to those who know it. They can just enter it, and out of the box they will get another simulation that will work in another way, that will optimize with completely another parameters, but at the same time it will help those people. So for example, here we can add a new drone like Magura, but with 500 kilograms of explosive elements. but with the same cost, and run our optimization. And what we will get is that now it's more beneficial to use, 1 second. Yeah, so now it's more beneficial to use those new drones because like they cost the same, but have more explosive elements, and that's why we use them, and we destroy ship, like while in the previous time we didn't. Yeah. Okay, so let's come to the analysis part. So Tanya, please.
Okay, we conducted our optimization and analysis of results based on our assumptions, our specific weights of evaluation function. So these results that you see here, they are kind of flexible in some way because when you change characteristics of drones, for example, and when you change some other parameters according to your domain knowledge, you can get different results. But some of them are really straightforward. So here in the slides, we have two charts. The first one is average value of our kind of goodness function by target strategy. So here you can see that the highest value, highest average value has a closest critical part strategy, which is really logical because we have more penalty for the ship on its speed and hit probability when we attack closest critical parts. Parts are the second one, and ship is the last one because we just attack random closest parts of the ship. So the second graph shows us dependency of average value of goodness function on a number of drones. So it's really straightforward. Then the more drones we have, the better the result of our operation. So value of evaluation function is significantly bigger when we have 10 or more drones. So that's it for this slide. Let's move to the next one. On the second slide, we have optimal proportion of drones because we have kind of two types, Seababy and Magura. And for our parameters, we see that it's roughly 50-50, but Seababies should be in optimal scenario 57% and Magura 43%. So it's it depends on actually drone characteristics or specifications because Seababy are faster actually and can bring bigger bombs. So they are more efficient in a way if we evaluate success by game win and ship damage, but Magura are cheaper actually and more they are slower, so they have a higher probability to stay undamaged after the end of the operation. So, and second one is the average value of function by formation strategy. So as you see, the best formation strategy, according to our research with our parameters, is the STAR strategy because we have drones kind of on perimeter, if I'm not mistaken, of the ship, and it's harder to hit all of them because it takes time for the ship to rotate its weapons and rotate itself. While, for example, for the group, drones are really next to each other, So it's kind of easier to hit them all because you do not need to rotate your weapons and rotate the ship itself. So the group 1 is the worst one according to our experiment, and the star one is the best one. So for outcomes and insights, that's it. Thank you for your attention, and you can ask your questions here.
Thank you so much to Team 2. Let's give Team 2 the round of applause. Thank you. Any questions for Team 2? Questions?
Actually, I have one question. You said that you used genetic algorithms, and on your visualization, it is stated that you have some goodness function. Can you tell us more about this function?
Yeah, it's actually from evaluate slide. I guess the goodness function actually is the sum of this parameter multiplied by weights, and you can actually adjust the weights. So yeah, based on its value, we conduct our optimization of parameters.
I can add that almost all of them are bounded. All of these parts are their maximum is 1. And like Jones cost can be also negative, but also the maximum and the best parameter, best value is 1 for it. So it's also quite straightforward when we optimize this function.
Thank you.
Okay, and also one question from my side. So I think your analysis, and correct me if I'm wrong, assumes that your drones are already in the vicinity of the ship, so in the neighborhood of the ship. How you can incorporate getting there? Because now we're on news that Russian helicopters successfully hunt the sea drones, and you may lose many drones on the way to the ship. So can you incorporate in your analysis the path to get to the ship from the point of launch of the drones getting there? How many drones may be lost on the way, and stuff like that?
Yeah, actually we can do this, but it will be the good topic for future research and improvements of our environment.
Great. Thank you so much. Thank you to Group 2 again. So let's give another round of applause to the Team 2, and let's move to the presentation of Team 4, and after we'll take a break.
Thank you.
And glory to Ukraine.
Thank you.
Slava. Okay, Team 4, are you ready? Команда 4. Andriy, Ivan.
Hi everyone. We are Team 4. There are only 3 of us. Yeah. Let me share my screen and start. Так, все проспойлерил. Yeah. In case of this task, in case of this project, we decided to simulate path. Yeah. Simulate path, make it probabilistic, maybe many different iterations like that, and that's why we defined 2 paths of the 2 paths of the solution. Yeah. But first, let's discuss why should we even consider it, because there are terrains. There are terrains on the battlefield, terrains in the city, terrains everywhere, and what we can do is to optimize how we move through these terrains, move through this map, and it's a really huge and versatile topic because it's not only military use, it's civil use. It can be I don't know, anything like traveling, through mountains, or if you're talking about versatility, it's about not only humans, we can consider pathfinding in some different occasions for some robots, drones, etc. Yeah. How should we create the path, the optimal path? We should simulate. Simulation is human safe. We do it on computer or maybe with some robots like that. It's highly extensible. It's not, as I said before, it's not only about humans. Yeah, it's even vacuum cleaners. Yeah, like I have in my home. And yeah, that's what's about it. And who can use it? Military, civil people, and yeah, maybe children even. Okay, here is our solution. I want to say that this is already a prototype. Yeah, but we will show it like that. Let me maybe want to explain what we have here.
Yeah, okay. Well, I'm Andriy. I was responsible for the UI and connecting all of the parts of this project together and make it intuitive to use. I hope I managed to do it. Well, how we expect the user to use it? Firstly, what you can see, it is a map, and you choose the location what you want. You fix on that, and you choose detailization level. You put allies, enemies. Enemies are treated like the finish points. You choose like power. It is only for prototype. Like later, you could choose unit type, how many, and other configuration. And after that, you run analysis. And what is the analysis? As a result, you get the correct coordinates with the minimal weight, with the minimal pressure you to go and try. We avoid surfaces like water or hills, or even like if we're talking about scalability, woods and other.
Yeah, and Andriy.
Hello, everyone. My name is Andriy, and one of the possible solutions was probabilistic approach, kind of Monte Carlo simulation. Yeah, unfortunately, I have only this dummy image, but anyway, so the goal was to find optimal path using many iterations. So I simulated the movements of the units. So on this beautiful image, you can see the two types of units on the left and on the right. So they move from west eastwards, and the algorithm considers, as was mentioned previously, it considers terrain. To be more specific, it considers elevation and presence of water. So if the only option is to cross water, then specific unit crosses the water. Otherwise, it tries to move towards the enemy units using the path with minimal elevation, and also if the elevation is like algorithm chooses random direction, and therefore, after many iterations of the simulation, we can decide which path is optimal. So I don't have good metrics to show, unfortunately, because when I considered all the stuff that I described, the algorithm no longer worked as expected. So so this is like there's some work to do to gather some metrics, etc. But anyway, it was a great experience to try to implement this with all the possible limitations, such as our team structure and deadlines. So yeah, that's it from me.
Yeah, was written to me, and my task was the second solution. It was reinforcement learning, as many of you who did it too. Yeah, I wanted to say how awesome it is, but you already said it, and yeah, all I can say that the solution. Here you can see the actual solution, the actual testing on some random sample. And what it does, it captures the terrain. Yeah, it's of course it considers enemy position change that would be quite hard with classic pathfinding algorithms. It builds paths through enemies, trying to maximize the harm and minimize its health loss. Is that's why you can see that these units just eat enemies and go further, to eat more. And the main point is that the complexity of realization is hidden. It's hidden by the properties. We just generalize it. So that's why this application is so versatile. Yeah, it can be tank. It can be, I know, the guy who runs pretty fast, like these dots here. Yeah, that's what about it. And core features here, it's of course versatility, it's deep terrain consideration, and the third part is from the previous slide. I forgot it to delete. Yeah, and what is next? What is next? The main thing that we wanted to implement, but unfortunately we couldn't. It was cooperation. It was cooperation in reinforcement learning. I believe it would lead us to some maybe not unique, but interesting, quite amazing things. Yeah, if you see how these units cooperate to win, and to maximize their health, because right now every unit is for himself. But anyway, in the end, they win. That's all.
Hey, thank you to Team 4. Let's give Team 4 the round of the applause. Thank you so much. Any questions for Team 4? Questions? So, okay, I will ask a question. So can you incorporate, or did you try to incorporate in your analysis the minefields, not only the terrain, but also the minefields or any other obstacles that may prevent you from finding the optimal path? Мінні поля пробували.
Your microphone is off.
Okay. Can you hear me?
You're on mute, yeah. Actually.
Yes, their microphone doesn't work.
Yeah, Ivan, Andrei, you're on mute. You can unmute yourself. Yeah. Ivan Andrei, you're still on mute. Так, включіть мікрофон, будь ласка.
Oh yeah, I'm here, but I cannot hear you. Yeah, unfortunately.
So can you incorporate the minefields in your analysis? Мінні поля можна інкорпорувати в ваш аналіз?
Yeah, I got a question, and I believe yes, because it will be a part of the state of this Q learning model. That's like the wall, or yeah, we'll just give huge negative rewards to the one that's who wants to step on minefield. Yeah, but I believe he knows that he shouldn't do it. Yeah, that's why the answer is yes.
Okay, thank you so much. Any other questions for Team 4? Yeah, in that case, let's give Team 4 another round of applause. Thank you so much. And we will take a break, and let's reconvene in 9 minutes in 18:55 for the second round of presentations. So 18:55. Yeah, thank you, Darina, for enabling the recording. So the next will be Team 7. So Team 7, please.
Yeah. Can you mute, please? Thank you. Hi everyone, and we are presenting our first project, which we called Assault Simulation. I'll explain in a few words why. So let's go to the scope. We started with analysis of the domain for the project, and the first thing that we found that military simulations actually persist for 2 centuries already, and they were invented somewhere in Prussian army, and since then they are developing, and so on. There is a lot of information, and many platforms and many solutions were developed along all this long period. At least 2 enterprise-level platforms were developed, and they eventually became even standards, which are employed by US military and NATO. So we reviewed these architectures and realized that they are way beyond the scope we can implement. So we changed our scope. We actually scoped the project to become a simulation of an assault of our forces onto enemy lines. In this scope, we apply several ML-based algorithms and compare the results from what we have seen. Let's have a look at the architecture. Architecture is based actually on Pygame with a session which could embed one of the algorithms. They're replaceable, and we added some external API, which we call Delta API. In fact, it's not Delta because we don't have documentation for Delta, but we created an API which provides an information for the enemy units, some sort of observations which are given with certain probabilities, and on that we actually try to calculate the result of the simulation. So let's go to the next slide, and I hand over to Vitalik for the environment part.
Yes. So first of all, let's discuss something about the Delta API. So as was mentioned, we didn't have the documentation for this API, so we tried to design our own clone for this API, which supplies enemies units with the location and the defined probabilities that are calculated from the automated computer vision preprocessing. Also, the important part of our project is the basically engine and the units. So in this approach of Wargames simulation, it is based on the abstract objects and their interaction between themselves. And we decided to try to get these simulations as close to the real life scenarios as possible. And it's really necessary to have an environment with necessary military objects, their properties, their applications in the combats, general laws of physics, and time discretization for logical step-by-step development of actions. So one of the solutions for this engine is to use some well-known verified open source engines like Unreal Engine or Unity. But for this baseline, we decided to develop our own engine that is completely developed in Python. And for simplicity, to check whether this simulation approach find any relevant strategy or not. So this engine operates with units for both allies and enemies forces, and take into consideration the map of this environment. And the main functions of this engine is to plan actions for units for each step, move these units and track their locations, scan all the ranges for possible attacking and targets, select proper targets for the next attack, also generate some random numbers for probability that is taking part into the attack to regulate the probability of destroying. And it's actually really important to calibrate these probabilities so it will be representable. Also, this engine calculate whether the enemies was destroyed or not as a result of the attack. It also monitor units and are they still alive, and calculate total strengths on each step. And in result, all this simulation history saves in logs files with information about the total reward, and it can be represented as further manual analysis and representations. Next, please. And here is, you can see on the slide the type of visualization. So this is a visualization of a map with some terrain and the units on it. And also you can see the marks of the strengths for each side. And later you can see the visualization on one of the scenarios.
Okay, so in our project, we use several approaches, a couple of reinforcement learning algorithm and Monte Carlo simulation. I will tell you a little bit more about the last one. Monte Carlo simulation is a computational technique that repeatedly generates random inputs and calculates outcome. And in our case, we randomize moves, target selection, and damage. The main advantage is scaling. Like once we had our model defined, we can adjust the setup, some initial data, adjust the terrain, and compare the results and make some decisions based on the results. Also, by considering range of possible inputs, it removes uncertainty, and it is actually pretty easy to interpret and make some conclusions. The main disadvantage is that it is highly dependent on the assumptions that we made with corresponding probabilities, and in order for it to be applicable and like a real have value in real life, we need to have a lot of historical data about like units interaction, about the probabilities, and so on and so forth. And another disadvantage is computation intensity. Like with the increasing of the complexity of the models, computational cost is significantly increasing. On this slide, we will have a simple comparison of simulation results. So we have two setups. We see that enemies have the same units, but for allies in the first setup, we have one more tank. And next, we will see the result of outcomes by running 100 simulations for both cases. And we can see basically the impact of having one more tank onto the overall win rate. Also, another important metric would be the remaining units. It's our so-called fighting strengths. And on the left, we have the remaining units comparison overall. And on the right, we have the remaining units in the victorious simulations, which should be also one of the most important metrics. Next, we'll present Q-learning approach, and Nazar will tell you more about it.
Okay, so I will briefly explain Q-learning. So first of all, comparing it to Monte Carlo simulation, we have some major differences. First of all, while Monte Carlo makes simulation, like simulates all possible scenarios randomly, in Q-learning we are maximizing the rewards. So we are basically searching for the best solution in our particular problem. Regarding rewards and how they are defined, for instance, rewards are given to the model for correct moves, and negative rewards are given for wrong moves, for allied deaths, and for losing on time. Rewards are very important because they basically define how our model will decide. And so basically, it is very important to maximize the correct thing, and there is no clear way to design them. And this is one of the disadvantages in Q-learning. And also, I want to say why we decided to use Q-learning in our particular problem. Since we decided to use discrete space for our problem, it was already a point to use a Q-learning approach, because it mostly works with discrete action spaces and states. However, overall, it is more a disadvantage than advantage. Another one of the advantages is its convergence, and with enough time and computational resources, we can find the best solution. On the other hand, we might have some problems with convergency due to large spaces or small explorations. Next slide, please. So when we could use it and what can we solve with it? So imagine a battlefield scenario where we have critical decisions and they are multi-phased. With Q-learning, Q-learning shines in such environments. We can handle complexity of decision making because it navigates through numerous variables in our setup, through terrain, through enemy positions, to recommend an optimal action, providing the commander's strategic insights. Moreover, in the realm of strategy optimization, Q-learning plays a pivotal role. It aids in maximizing rewards by constantly learning from past encounters and evolving strategies accordingly. This allows us to decrease possible risks and to maximize our chance of success at the same time. I would also say that, generally speaking, in a smaller scale conflicts, it would work better because there are some difficulties with Q-learning in large spaces, as I already mentioned. But in Q-learning, in smaller cases, it proves to be a valuable asset because of its ability to provide rapid and precise insights or some adjustments. Next, we'll discuss Deep Q network, and I'll pass the word to Maxim.
Yeah, thank you, Nazar. So about Deep Q network. At its core, Deep Q network is a reinforcement learning algorithm which combines a Q-learning approach with the deep neural networks. And the first thing that this algorithm solves is much better handling high-dimensional spaces when we compare, for example, for some traditional methods or with Q-learning methods. it can manage much higher dimensional spaces. Also, these algorithms, also the pros of this algorithm is its generalization. It can, by using deep neural networks, it can generalize on similar environments. So we can use some similar environments or skip some parts of this environment and just give the opportunity to generalize for this algorithm. The next one is efficiency and stable learning. This algorithm, by using replay methods, can break the correlation between consecutive samples. And also, these algorithms could work with the offline environment. So when we don't have an opportunity to get a real data, we can use a fixed data set of experience. But of course, there are some cons of this algorithm. The first one is that it requires a lot of samples, and also it's much more computational required. That's due to neural networks. And the next two of them is partially observability. So this method will struggle in partial environment where not all actions is open to it. And also, as Q-learning, DQN limited to discrete action spaces. Next slide, please. So where we can use this algorithm. The first one, as I said, is highly effective in environment with large high-dimensional state spaces. So it's really well-suited algorithms for challenges like video games or any applications with images or videos. Also, we can use these algorithms to discrete action spaces, especially scenarios requiring a series of decisions to achieve a goal, like, again, video games or navigating mazes, for example. And in terms of practical solutions, this algorithm can solve really complex problems due to its nature of that's created by a deep neural network. Yeah, I pass the word to Vitalik. Oh, yeah, let's go to the next slide.
I guess to me.
Yeah. So
okay. So let's go briefly through the simulation results. We took a sample setup, and with this setup, we want to show you the results of Monte Carlo simulations. So with that setup, we've got a measure of roughly 60% of retreats, and others like and 15% of defeats. But comparing to the same setup on Q-learning, after reaching a significant amount of episodes, let's say sufficient amount of episodes, we've got a victory in almost 15%, 51% as actually, which shows supremacy of Q-learning over the Monte Carlo simulation. And from here, we can make some direct outcomes that, first of all, it is possible to simulate a battlefield environment. Of course, we have to include much more factors than we considered in our scope, and it is also possible to actually judge the balance of forces. To judge a balance of forces when we have simulation of some tactical situation. So let's go for the further problems.
Yeah, I would like to add a few words about further improvements. So basically what we can improve here, we can add more units, we can add air forces. Also, we can add some coefficients and some masking and like basically more interaction with terrain, and also calculate damage in based on the terrain which is surrounded, which the unit is surrounded by. And also we can try a few other approach like GNA, GAN, and QMix. And in the end, I would like to show a demo. This is a best case scenario from Monte Carlo simulation. Yeah, and that's it. Thank you for your attention.
Thank you to Group 7. Let's give Group 7 the round of the applause. Thank you so much. Any questions for Group 7? Okay, so question from my side. In your example that you just shown, what size of the operation did you model? What was the size of the grid? And how many units, soldiers you had in your simulation?
Can you mute, please?
Yeah, of course.
Yes, so the size is 20 by 20, and the units is actually the setup one that I showed in here. So the fighting strength of our allies is 6, and the fighting strength of enemy is 4.2, because since it's offensive operation, we are at the beginning it is in disadvantage, so we need more units to have a approximately good win rate.
And what maximal realistic size that you can model? So you did 20 by 20 cells, so which is 400. So what do you think you can bring it to in terms of the grid and in terms of units?
Actually, I think it can be like any size, but it can be tested. It should be tested first, because for some simulations, we need to test the terrain, because if we have like a cell which would be surrounded by the terrain that the unit cannot pass, for example, hills, and there is one cell like surrounded by hills, and the tank goes to this cell, it would be almost impossible for him to get out, and we can get stuck. So it's we have actually like a slight problem with terrain situation, which we should take into the account.
Okay, thank you. Any other questions for Team 7? Okay, in that case, thank you to Team 7 again. Let's give them the round of applause, and let's move to the presentation of Team 5.
Hey, colleagues, do you hear me? Do you see the slides?
Yes.
Okay, we can start. Greetings, everyone. I want to present to you our team's course project, which is designed to help our military forces quickly analyze and make decisions regarding managing strategic air defense systems. Before we begin, I will briefly introduce our team. 4 people were working on the project. My name is Yuri, and my colleagues are Igor, Bogdan, and Denis. We can start now. Our presentation will be divided into 5 logical parts. We will begin with a more detailed description of the problem, and then briefly review the key results we have achieved. The next point concerns our algorithms work and valuable insights from the analysis we have done. And in the end, we will discuss the existing limitations and our vision for the future development of the solution. So, what the problem are we solving? We all are involved in active warfare, where airspace defense plays a crucial role in the long-term dynamics toward victory. Ukraine has a limited number of strategic air defense systems. So their optimal placement dramatically influences the outcomes of enemy attacks. Therefore, there is a need to create a framework for making rapid decisions regarding the optimal deployment when needed. For example, such decisions may be made in case of a decrease in the number of available fire stations, changes in their characteristics, or, for example, the emergence of new aerial targets from the enemy. Additionally, the enemy is constantly changing its attack tactics, so the overall environment for decision-making is too dynamic for simple empirical approaches. How did we address the described problem? We created a solution based on simulations. We can run a big amount of simulations and assess various decisions regarding the placement of strategic systems. Then we are finding the optimal deployment scenario. The algorithms are fast, so all that is required from end users is to give new inputs to the algorithm and quickly obtain new analytical results. It is important to note that the developed solution can be applied at different battle scales, both at the level of the entire country, which we will demonstrate today, and locally within a specific combat region. Apart from the simulations, we developed and tested 4 different approaches to finding the optimal configuration. We analyzed the results and, based on them, set several strategies for using the fire stations. Ultimately, we choose the best strategy, which my colleagues will discuss in the following slides. To understand the next slides, it is also important to note what we used the same conditions for all our simulations in order to compare the outcomes. Next, I invite Igor to talk about how we simulate air combats.
Let's discuss some details about our simulation. In this simulation, we used characteristics of real anti-aircraft systems, which Ukraine uses right now. For example, S-300, Patriot, Buk, SAMT, and other. Characteristics include detection range, strike range, speed of the missile, and also probability to detect and destroy target. Also, we simulate attacks with different types of targets, such as UAVs, cruise missiles, and ballistic missiles. All of them also have their speed, range, and possible trajectory. Destination points of air targets are real objects like stations, military bases, aerodromes, and other which could be selected by our enemy to attack. All information about coordinates has been taken from open sources. Start points are different for different types of targets. For example, UAVs Shahid could be started from Bryansk region, Kursk region, Primorsk-Akhtarsk, and Chauda in Crimea. Strategic missiles have start points in the area of Caspian Sea and calibers in equator of the Black Sea. Also, we consider the targets have different trajectories and routes, and added some random components into the building of the route, which allows us to model the most part of possible routes. To evaluate efficiency of the setup, we calculate % of destroyed targets and also critical damage for our objects. Our simulation includes visualization of the routes of targets. Blue routes display destroyed targets and red display survived. Also, you can see strike ranges of every system. On this image, we have just random positions of the systems, and our goal is to find optimal placement, which allows us to maximize % of destroyed targets and minimize critical damage. Let's go on to our algorithms.
Okay. Ultimately, our goal is to use each air defense system as effectively as possible to achieve the highest air threat destruction rate and minimize the total damage. A system has the highest probability of working with the maximum capacity only in places when a significant amount of air targets are present. So the fundamental idea behind this approach is to search for dense areas in the simulated data and locate systems in such areas. Useful dense areas could be from the following 2 groups. First ones are areas with many routes of air threats, and the second ones are places with a large amount of valuable ground targets. So we generate a grid of possible air defense locations and then evaluate each point regarding the potential effectiveness. The best points are recommended for deploying the best available systems by their characteristics. This method gives us an average of 78.5% of destroyed targets for 15 randomly generated attacks. The respective criticality score is 1459. We can see that this is significantly better than our base case when we deploy systems randomly, as Igor said. However, this is not the best result, and I invite Denis to tell you even more.
So the second approach we have investigated is heuristic search. As previously, we split the territory into the grid of cells. Then we calculated specific characteristics, flight rate and critical rate per each cell. Based on these values, we test an approach on the three strategies. Strategies one is deployment along the most popular routes. The second strategy was deployment along the most valuable routes. And the third one is like a combination of the first one and the second strategy. For implementing heuristic search, we have chosen a genetic algorithm. The main idea of this method is we start with various solutions, let the best ones survive, mix them to create new solutions, and iterate this process to evolve towards the best possible solution. I would like to stress that it includes a few probabilistic parameters which can have a big impact on the result. Due to this nature of method, each time when we execute it, we get different solutions, but at the same time, it converges, in our case, to 75–85% of accuracy. So after the testing of it, we can conclude that the third strategy is the best one. It provides approximately 83% of destroyed targets and about 850 critical damage. If you look at the diagrams, we can see that it provides destroyed targets in range from 79 to 89% and total critical from 400 to 1,200 score. Now let's move on to the third approach that we have investigated.
Yeah, the third approach is based on AI solution. What we did, the main problem of this task, that our computational function is hard to calculate and it takes a lot of time to calculate it. So we decided to train a small model which could simulate our results, but based on some subset of data, which is much smaller than the subset which we will in future use to iterate and find the best system. We will generate, after we train a model, we will generate an iteration with random locations of anti-air systems, and then due to the fact that our model could give bad results, we will select top X location from each iteration, and then we will use these locations, which the model decided is the best to calculate the best one from this subset. And this could improve our speed by hundreds of times, so we could simulate millions of simulation by using this approach, and it will help us to choose better approach much faster. This result will give us 88.3% of destroyed targets and critical damage 634. And next approach. Yeah, and now we will go to the greedy algorithm, where instead of placing all systems at once, we will try to set them one by one. The idea is that when we want to set one system, we will try to find the best position for it. And then for the next system, we will try to find the best position based on the locations of previous one. And this will help us to calculate better position for each system. As we could see, the results of this model is 92.3% destroyed targets and critical damage is 440. Next slide. So now we could see the results of greedy algorithm, and we could see that the first what we can see is that it decided to set some anti-ballistic air systems near the Belarus and near the Crimea. That's because most of the ballistic missiles are launched from this area, and that is why the other are located near the borders. And also we could see that most of anti-air systems are located on the east of our scenario. This is because most attacks are launched from the east, so it's better to locate our systems there. Yes, thank you. Next.
Now, let's talk about the most interesting and analytical insights from our investigation. Based on analysis of simulation results, we identified three potential strategies for defense against air attacks. The first, deployment of system along the most popular flying routes. The second, deployment of systems that covers the most valuable targets. And the last one is deployment of system along the state border. And of course, combinations of these strategies. The recommended deployment method is, of course, those ones that provides the best result. In our case, it's one-by-one greedy placement algorithm. The results that we got during the testing prove that it can provide the maximum efficiency of each available defense system. So 92% of destroyed air targets, the best provided metric that we received during the test of each proposed approach. It was provided by one-by-one method, placing strategic systems along the border, while the mid-range defenders remain inland.
Also, we have to say about some limitations of our simulation. Currently, every system has unlimited amount of missiles, which doesn't reflect possible real-world logistic situation, even for strategic systems. Also, we don't simulate situation when our enemy is trying to destroy our systems. And we don't consider environment impact. But for the future development and improvement, it is possible to make simulation more accurate by using elements of game theory and considering more factors like as environmental impact and information from our enemy. Thank you for the attention. We will be happy to answer for your questions.
Thank you to Team 5. Let's give Team 5 the round of the applause. Thank you so much. Any questions for Team 5?
Can you guys repeat, please? What about was your roads like static, like just based on the history, or dynamic, like they also adjusted by your new strategies?
Hey, Igor, could you tell? Or...
So start points for our routes were based on the information from open source, and also like destination points were selected from a list of like possible targets. And when we are generating routes for our targets, we also consider information of which type this target is. For example, ballistic targets are moving like forward on this map. Also, UAVs are moving with some turns during the route, and we just add some random component to the generating of this route, and we didn't use like information about previous routes from the internet.
Okay, thank you.
Thank you. Any other questions for Team 5?
Yeah, I have a short question as well. So, do you consider a probability of success for striking the missile?
Yes, we have probabilities for different systems, and also like probability of detection and probability of destruction. Also, we have probabilities for different targets. For example, probability to detect Shahid is lower than probability to detect missile. And also, for example, probability to destroy ballistic target is lower than probability to destroy normal.
Yes, and ballistic targets can be intercepted only by specific complex that have such abilities, for example, as Patriots or SAMP-T. Okay, Alexander?
Yeah. Okay, so looks like no other questions for Team 5. In that case, thank you again to Team 5. Let's give Team 5 another round of applause for the great presentation and great research project. And let's move to the presentation of Team 1, the last but not least. Team 1, please.
Hello, let me share the screen. Can you hear me, by the way?
Yeah, we can hear you. We can see your screen. Thank you.
Slideshow. So let's begin our project called Talk to Your Theme. Here's the authors, and let's begin with our presentation. I divided this slide into 3 parts. It is product description, first of all. We wanted to make operation simulation easy to run and understand. And from user needs, we outlined need for interaction with various simulators that should be done easy. We want a user wants to understand underlying concept easily and in one place. He doesn't want, or she doesn't want to interact with various APIs or documents available due to their vast size. And from the product solution, we want to use LLM to interact with various simulators conversationally, like a chatbot, ChatGPT you've seen, but with simulators. And we want to give to user multiple simulators available to understand the situation better and to grasp a wider picture of it. And we want to run the solution locally without internet available. And we're moving to the last part of this slide, which is about implementation and challenges. And we wanted to use an open source LLM because it can run locally and it doesn't require any internet connectivity. And we wanted to use both reinforcement learning approaches and Monte Carlo simulation approaches to enforce to ease understanding of our simulation to end user by widening number of simulators available in our application. And moving on to our agenda, it is also split in 3 parts. It is about product and historical data overview, operation, simulation methods such as Monte Carlo and RL, as I mentioned it before. And the last but not least is our LLM assistant and demo. I pass my word to Yura and let him speak.
Thank you, Roman. So at the beginning of our project, we faced a dilemma of selecting a set of variables that we wanted to implement in our simulations. We had many ideas, but we wanted to choose such variables that will impact the outcome of the battle the most. So after some research, we discovered that the US Center for Army Analysis, or CAA in short, actually faced the same similar problem in the past. In general, CAA performs analysis and employs computer simulations in order to analyze and optimize existing processes in the US Army, assess the risks and simulate possible future conflicts, as well as one of the key features actually that they can portray decisions by commanders under a variety of scenarios and conditions. CAA believed that historical data of past battles could provide insights into which would enhance the ability to more accurately simulate possible future battles. So in 1984, CAA, together with Historical Evaluation and Research Organization, or HERO in short, started a research of over 600 historical battles that took place from 1600 AD to 1917 3 OD. And they had an objective of determining and evaluating a set of descriptive factors which would influence the outcome of the selected battles. As a result, in 1990, they comprised a dataset called Database of Land Battles, or in short, CDB90, with over 50 such descriptors, which they came up with on themselves and defined and evaluated. So CAA divided all of their factors into 7 groups, but after our further exploratory data analysis, we separated them into 3 categories. First category is factual data. It contains descriptors like battle name, location, result, etc. Second is objective data. It includes factors like terrain, weather, total personnel, equipment, casualties, and so on. Basic feature of these factors is that they can be actually defined. And the third last group is subjective factors. They were assessed by historians and military experts, and these are the factors like leadership, experience, planning, etc. These factors were defined using an enumerated range from -4 to 4, and each value corresponds to level of advantage or disadvantage that particular site has. So such factors contribute to a big portion of this data set, and factors like this can neither be assessed during the battle or even before it. So since we can only evaluate them after the battle, and we have to have the knowledge of situation on both sides, we cannot really apply them to our simulations. And this is why we decided to disregard them and focus on objective ones. In particular, we chose personnel amount, general army composition, defined several unit types like infantry, tanks, and artillery, and also defined constraints on the environment, as well as some special ones which are unique to each method. And now about our methods used, I'll pass the word to Ivan.
Thank you so much. So first method that we were using, it's like agent-based modeling. We were talking about it today, and here is just some example. It's Shannon's model of segregation, and we can see that by changing some of the system is also changing so much, and here is like with the 30% threshold of number of neighbors from the same fraction which agent would like to have. Another approach that we have used is Monte Carlo method. So Monte Carlo method was first developed during the World War II, and the idea is to simulate in our case, battle like 100 or 1,000 times, and to take some statistics from it. So based on these two approaches, we have developed a special Python module, which is on the next slide. Here we can see that we can specify territory with different heights. Here heights are like has different lightness, and so the higher is lighter here. Also, there is like a minefield with a different amount of mines. We can see them like purple points. Also, there are different units such as infantry, medics, and artillery, and all these units have different abilities from like database. Also, our module provide real-time visualization, and damage here is not like scalar, but it's calculated depends on the heights, for example, and some units features. Also, the interesting things here is that we specified this artillery. It has like a range from the whole map, but it has like damage delay. So after the simulation, we have different results, like analytical results and statistical results. Here we can see like number of units alive during the simulation and damage distribution by each unit. Also, our module supports Monte Carlo simulation, as I mentioned, and for example, here, after 50 simulations, we can see how much alive allies we expect to have. And on the right side, we can see a relative loss of soldiers as function of initial forces size. And we can see that with the bigger army, our losses are like less. So as conclusion for this module, we can say that it's like easy to specify different land space and expected minefield distribution. We can combine units in different groups. Also, I would like to mention that in one group could be like 50 or 100 units, and in our simulations, we were simulated like up to 200 units with the given roads. Our module provides different analytical and statistical information, supports Monte Carlo method, and it's easy to scale existing functionality, and it's possible to add more features and units. So another approach which can be used, as Monte Carlo is not like one option, will be discussed by Yuri.
Thank you, Ivan, for exciting presentation for your part. So let's discuss some interesting thing. We have the Monte Carlo and reinforcement learning. They both are pretty cool approaches, but Monte Carlo has several problems. First of all, like what I think is the most, it's not always the best for every problem. It's not applicable for every situation, like in optimization of battlefield. The second one is it's too expensive in resources. Like you have to have a really powerful computer to simulate a huge Monte Carlo simulation, like for, I know, thousands and thousands of battles. And overall, it's not so accurate, like because some tail events cannot be estimated. On the other hand, reinforcement learning can be used more like precise, and it can be applied to more wide range of problems. Please, next slide. We've been talking about it on previous presentations a lot, but just a quick overview what reinforcement learning is. We have the three main like things, no, four. Like we have the agent, we have the environment, and we have the interactions between them. If agent takes right actions that these environments describe, he receives the positive reward. And in other case, he receives the negative reward. So in the end, we'll have some agent that can behave in our environment, and receiving only the positive rewards. He will find the best steps and best actions to, I don't know, receive the cake. Like if we're talking about the dog. Next slide, please. Our solution is pretty simple but effective at the same time. We have the Pygame, and it runs the main process and the gymnasium environment. And we have the predefined data, some enemies and some allies. And all the environments, like our environment is represented by the map. I will show it later, like the real one. The rewards are decided by the following constraints, the main ones: terrain, flank, enemies, and the weather. The flank defines like whether we go on the left or the right. The weather decides what is the summer or the winter for simplicity. Like we don't need to take the wind speed or the humidity or temperature. It's too complicated. We just, for simplicity, we take only the season. And the enemies. If the group step on the enemy's cover area, it received a very, very negative reward. Next slide, please. This is the way how we created the map. We used really exciting algorithm. And I believe, and that's why this algorithm, this key learning that we used, can be applied to any terrain and any map. That's it for now. Next slide, please. Now let's talk about LLM, and I believe Roma will introduce you to this magic.
Okay, so let's continue our LLM magic. As a first step of our application flow, we have input gathering, and we gather such input as user question or query, as we call it, and a piece documentation, such as documentation for Monte Carlo simulations or AP documentation for reinforcement learning simulator documentation. As a next step, we have to classify our intents, because we want to not only give user access to simulate certain environments, certain scenarios, operation, and so on, but also to learn more about the specific documentation, such as how Monte Carlo API work or how reinforcement learning API work, so user can interact with it more easily. For example, which variables are available for certain simulators. And you can see the examples, and I will show it later on demo due to limited time we have. And later on, we process our intents. For example, if you have a conversational chain, we call it, we go on with talking with our user about the documentation. And if we want to simulate our environment, we proceed with generating an API URL, and after that we call it and generate a response based on response from the API. By that, we mean some magic happening under the LLM, as it calls underlying APIs, and gives us a response in a conversational manner. And as a last step, we run as a simulation, as I said, and we visualize our results. Here's our architecture design. It is also divided into 3 parts. On the left, you can see intention classification, where we classify whether the intention of our conversation would be conversational, as I said. More about military simulations, more about learning more about documentation or simulators. And the other one is about classifying to running the simulators actually. And we also classify whether it would be a Monte Carlo simulation or a reinforcement learning simulation. And after that, we summarize the result gained from the API. We prepare our answer and we add it to the chat memory. As you can see, we went through classification, processing, and to result consumption. And here's our implementation. I won't go into those fancy pictures as they may seem too complicated, and I would rather prefer to show you a demo to not for this presentation not be so boring and technical. So for example, on the left, on the right, sorry, you can see a simulation bot chart we prepared using a Streamlit application. And let's ask the bot to describe simulators available. It will take some time because we are using a local LLM, not the cloud one. So it is running locally on my laptop, and yeah, it would take some time thinking. Let's wait a little bit more. So here's a documentation for our APIs. As I described to you, we have a Monte Carlo and RL simulators available, and the app described them to us. So let's simulate a small scale battle with, let's say, 20 soldiers and 7 medics. And as a small-scale battle, we expect to run simulators using Monte Carlo algorithm rather than reinforcement learning, because it is more statistically based and more operational based level. Yeah, and as we can see, it called the API and started a simulation to according to our parameters. Let's try to simulate something with our RL application. For example, we want to run simulation on group gamma. With strategy safe on central flank. And from that, we expect to run a reinforcement learning simulation as it suits parameters, as those APIs have a different ones, and the previous one didn't have a specific groups. And as you might recall it visually, it comes similar to Palantir application, but this one is a much more basic one. Let's write a little bit as it thinking. So as we can see, it started simulation with group gamma, not alpha or delta, on central flank, and it shows summer as weather because we didn't specify a weather, as my colleague reported earlier, and it shows a default parameter. We can choose another group, for example. And at the top, you can see the statistics, for example, the probability of defeating specific enemy groups. And yeah, let's wait a little bit to check it out on Delta group. And as you can see, it shows a Delta group and it shows right flank, as I said, and it changed weather to winter. And on winter, as Yuri said, the weather is a bit more difficult and it is tougher for the agent to go through each of the cells as it is snowy out there. Basically, it is it for our demo. If you have some questions, you are free to ask me, and I'm happy to share this presentation with you.
Okay, thank you to Team One. Let's give Team One the round of applause. Thank you so much. Any questions for Team One? Okay, so I will have a short questions.
Yeah, but like you can start and I will proceed after you.
No, and we probably don't have time for a couple of questions, so please go on.
Okay, I was interested about like LLM, like why is it local if you still use like APIs of your other like reinforcement learning and
can you hear me? So
Yes.
if you take a look on our architecture, we don't use any internet APIs. We use APIs stored locally if you're talking about simulators, and we use LLM file, and through Llama CPP we store a wrapper with LangChain, so it is available locally, and we can run all this magic stuff on our laptop without internet connectivity.
Okay.
Okay, any other questions for Team One? Yeah, if not, let's give Team. Sorry.
Okay, I have a small question.
Please.
Do you believe that reinforcement learning can simulate the battle with like many agents? As far as I know, it does not support for now like a big battlefields with many agents. It only support like tens.
It only supports like now for now it supports only the single agent training, but also there are like multi-agent reinforcement learning algorithms, like ways to implement it, but it will take much more effort, I think, to understand how they should behave between each other, because each of them should have the reward, and we also should predefine the number of it, because we cannot have just a random number of agents. We should clearly predefine them to the before running the environment.
Okay, thank you. I thought just there are more agents in your system.
Okay, thank you.
Can you please ask again?
I just thought that there are more agents in your system, so thank you for the answer.
No, there are only one agent. The other ones, like the enemies, moving by the specific trajectory. They are not training on anything, so they don't receive the reward. The only one who receives the reward is the blue dot that we choose from the LLM.
Okay, thank you. Now I understand.
Okay, thank you again to Team One. Let's give Team One the round of applause. Thank you so much. And now let's also give the round of applause to all of you, to all teams, for the great presentations and the great course project results. So thank you for taking the course. You did a great work in this course project, so it's exceeded a lot my expectations. So different directions, simulating battlefield operations, sea drones, air defense systems, and other interesting tweaks in this. So I hope that some of the teams may decide to make those practical and convert the MVPs into something that helps Ukrainian army to save lives and to win the war. And again, I wish you all the best in your future endeavors. Thank you for taking this course. Thank you for doing the course project. I hope the course was useful. Take care. Дуже дякую. Слава Україні.
Героям слава.
Героям слава.
До побачення.
До побачення. Дякую.
До вечора.